Welcome back, everyone. I am absolutely thrilled to have you here for this explainer. Today, we have a highly specific, incredibly crucial goal. We are going to master the mass energy equivalence topic, that famous E equals mc squared, specifically for the Cambridge Physics 9702 exam. But we aren't just going to look at the math, no. We are going to treat this like a symphony conductor leading an orchestra. You see, to get top marks, you need to orchestrate your arguments. Every single paragraph, every calculation has to act like an instrument playing in perfect harmony. We've got the actual data, the real examiner reports, and we are going to dissect exactly what the experts are looking for when they mark your paper. If you've ever felt like you truly understand the physics, but somehow you just keep dropping marks on the actual exam, well, you are in the exact right place. We're going to fix that right now.
Okay, let's dive right into our agenda. We have a highly structured roadmap today to make sure we secure those maximum marks. First, we'll look at the mass energy exam trap. Then, we're going to cover mastering core principles and follow that up with a technical exam methodology. After that, we'll shift gears into critical analysis for top marks. And finally, we'll wrap up with some final examiner insights that could, quite literally, save your grade. It's a packed session, so let's get moving.
Section 1, the mass energy exam trap, and exactly how we go about avoiding common pitfalls. I want to start by acknowledging something right out of the gate. If you find this topic incredibly tricky to navigate under pressure, you are absolutely not alone. Let me paint a picture for you. Imagine two students taking this exact exam. We'll call them Alex and Sam. Now, Alex is super smart. Alex overloads their answers with raw physics facts, dumping everything they know about binding energy onto the page, but there's zero analysis. It's just a wall of text. Then you have Sam. Sam rushes. Sam completely misses the specific command word requirements, calculating a final number, but ignoring the actual question asked. Both Alex and Sam are going to lose massive marks despite knowing the physics. That is the trap.
So, why is E equals mc squared one of the most misunderstood topics in Physics 9702? I mean, the equation looks so simple, right? Energy equals mass times the speed of light squared. Just 3 letters and a number. But when the senior examiners sit down to grade these papers, they consistently report that this is an area where students just hemorrhage marks. The difficulty isn't usually in plugging numbers into a calculator. It's the specific nuances. It's knowing when to use atomic mass units, when to convert to mega electron volts, and how the concept applies across different, really complex scenarios like nuclear fission or radioactive decay. It's not just a math problem, it's a logic puzzle.
What's really fascinating here is that the top 3 mistakes preventing students from getting an A are entirely preventable. Straight from the principal examiner reports, here are the major warnings. Number 1, using the wrong approach for the wrong context. For example, trying to convert mass defect in atomic mass units directly using the speed of light instead of using the 931.5 conversion factor. Number 2, ignoring format and presentation. This is exactly what Sam does when rushing. And number 3, providing generic, non-specific answers. That's Alex's problem, writing a textbook definition instead of applying it to the specific nucleus in the question. Before we continue, subscribe to our YouTube channel, Ace the Exams, at aceexams_IGCS, to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
That brings us perfectly to Section 2, Mastering Core Principles, or what we can think of as the theoretical architecture of your exam response. If you want to build a flawless answer, you need a rock-solid foundation. And this is where we bring in our strategy, the Peel framework: point, evidence, explanation, link. You have to break down the physics assessment objectives and structure your answers logically. You can't just be Alex and dump facts. You need to make your point, back it up with mathematical evidence, explain the physics principle, and link it back to the command word in the question.
Here's a crucial definition derived directly from the syllabus guidelines: connected conceptual understanding. This means demonstrating mastery of precise definitions and causal relationships that can be transferred to unfamiliar contexts. Notice the exact language there. Top-performing students do not just memorize isolated facts. They understand the causal relationships. They know exactly why a mass defect leads to a release of binding energy, and they are prepared to apply that understanding to a hypothetical radioactive decay scenario they have never even seen before in their textbook. That is the Peel framework in action.
And this brilliantly illustrates our ultimate goal. As the principal examiner reports explicitly highlight, candidates referencing cross-topic connections achieve significantly higher marks. Your theoretical architecture relies on integrating mass energy equivalence with totally different areas of the physics syllabus. E equals mc squared does not exist in a vacuum. Think about it. An alpha particle is emitted from a nucleus. Suddenly, your nuclear physics question is actually a conservation of momentum question, because the alpha particle and the daughter nucleus recoil. When you tie mass energy into momentum or kinetic theory, you signal to the examiner that you are a top-tier candidate.
Now for Section 3, Technical Exam Methodology. We've talked about the theory, but now we need the standardized sequence. This is the highly practical, step-by-step procedural framework you should deploy for any calculation or data question they throw at you. We are going to take those red pen marks that Alex and Sam get, and we're going to transform them into green check marks. We're going to use what I like to call the physics success blueprint, rewriting answers with complete precision.
So the crucial point is applying this 5-step sequence systematically to every single problem. Step 1, identify the key elements by extracting data and decoding the command words. Step 2, apply the relevant principles. Maybe that's your Peel framework. Step 3, execute your analysis with completely clear working. Step 4, verify your results. Does a binding energy of 500 joules make sense for a single nucleus? Definitely not. And Step 5, present it all in the appropriate format. Every single time you skip one of these steps because you are rushing, you are literally leaving marks on the table.
Furthermore, strict presentation conventions matter. Proper headings, correct terminology, appropriate formats, and clear annotation. When you are systematically processing data in E=mc² questions, examiners demand strict adherence to these rules. It is absolutely not enough to just scribble the right number at the very bottom of the page. Are your units in mega electron volts or joules? Did you state the formula before plugging in the numbers? How you structure and annotate your reasoning is actively being graded. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCS and turn on all notifications so you never miss our weekly acing exam strategy sessions.
All right, let's jump into Section 4, Critical Analysis for Top Marks. This is all about differentiating a basic pass from a true top-tier score. The highest grade boundaries require higher-order assessment objectives, so we are going to run a little interactive workshop right now. Challenge 1 is a data scan. Imagine a complex physics data table showing binding energy per nucleon across different elements. I'm putting 60 seconds on the clock. In your mind, can you extract the core trend? Iron 56 is at the peak, right? Fusion happens to the left, fission to the right. Being able to scan and instantly pull that trend is what separates the best from the rest.
Now for Challenge 2. Let's find the flaw. We can contrast the standard student approach against the ideal examiner standard. A standard answer to a comparative analysis question usually just identifies the differences. That's fine, it will get you a few marks. But a top-tier answer identifies similarities and differences, uses comparative connectives, and, crucially, supports each single point with evidence before drawing a conclusion. So if Alex writes a paragraph just listing facts about two isotopes without comparing their mass defects directly with calculation evidence, you've found the flaw. You have to elevate your response from merely descriptive to truly analytical.
Let's move to Challenge 3, Speed Writing. Look at how this framework lays out the action required for evaluating evidence quality. You need to identify limitations in the data. You need to question assumptions and provide alternative interpretations. If you had 30 seconds to write one perfect Peel paragraph on why the calculated energy release in a fission reaction might differ from experimental results, what would you say? A top candidate would mention energy loss to neutrinos or kinetic energy of neutrons. They don't just accept a physics scenario at face value. They interrogate it. They orchestrate their argument.
And finally, we reach Section 5, Final Examiner's Insights, featuring what we call the method mark strategy. If you take away absolutely nothing else from this explainer, let it be this. This is the most strategically important takeaway to carry with you into the exam room, because it's the ultimate safety net for when things go wrong under pressure.
Listen to this direct, incredibly emphatic examiner alert. Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. Process is just as important as the final product. If you calculate the mass defect perfectly, but then you accidentally forget to square the speed of light on line 2, your final answer is going to be completely wrong. But if your physics logic is flawless for the rest of the problem, the examiner actively wants to give you credit for that logic. But they can only award method marks if your method is actually written out on the page. Show your work.
To summarize, our complete physics answering system, our cheat sheet recap essentially boils down to 3 rules that guarantee top marks. Rule 1. Command word decoding. Always deconstruct the question first so you aren't rushing like Sam. Rule 2. PEL framework application.
Always show clear, undeniable notation and extract relevant data systematically. And Rule 3. Follow a time management matrix. You are putting your thought process on display, making it incredibly easy for the examiner to award you points at every single stage of the problem.
So, I leave you with this provocative question. Are you just memorizing the E equals mc squared formula, or are you truly ready to orchestrate a fully connected, top-tier exam response? Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here. Thanks for joining me. Keep up the fantastic work, and I will see you next time.